Okay. So yeah, you can view the lecture slides on the website and follow along if you like. All right. So today's talk, we're going to focus on the basics of an OS. If you're a master at Linux, you could probably leave the room. I don't want to waste your time. Some of the stuff I'm going to get to and at the end are some of the ways that rootkits are installed in Linux systems. It's not a complete coverage of that, but it's pretty good. So we're going to focus on kernel and user space. Permissions are an important part of any secure system. We're also going to go into firewalls and IP tables and how to use them and why those are important. And then file system quirks and behavior, common commands that are used for system administration and security, and persistence mechanisms used by malware, and most importantly, logs. But first, who heard about the vulnerability for Ruby on Rails that came out 2 days ago? 2 people? So this vulnerability was announced on January 8th, and it was discovered that this vulnerability allows attackers to bypass the authentication systems. So if there's a website that has username and password, they can bypass it if it's using this particular method. They can also use this vulnerability to inject SQL code and attack the database, as well as perform denial of service, but most importantly, to execute arbitrary code. The 3 things that are bolded are really what makes it so dangerous. A day later, public exploit code was released by someone else, just taking the ideas discussed, and this is what's vulnerable. On January 8th, they also released, this is the workaround, this is the patch. But about a day later, the exploit code was all released by someone else. And in a matter of hours from now, the exploit code is going to be implemented into Metasploit, and it's going to be an automated part of the Metasploit exploitation modules. That's how fast this industry moves. So I chose all these. You can go look it all up yourself, but I'm just trying to give you guys some perspective on how things move in this industry. Before I want to start the lecture, I wanted to revisit the disclosure debate. So we discussed last time the anti-disclosure, full disclosure, and all the eras basically that the industry has gone through. So does anyone have any opinions on the SCADA and PLC industry? Let me give you some info first. SCADA controllers and PLC controllers are things that control our electric grid, our sanitation for water. They control our flight control systems and radar. They control our traffic lights. They control our subway trains. They control a lot of physical things. And they are also part of basically our public safety as well as our national security. The problem is that most of these things the hardware is controlled by private companies. Private companies supply our power. They're not run by government in most cases. So the government can't just say, hey, you need to fix your security, because they're not obligated to follow what the government says unless it's hammered into law. And it's currently not, that you have to have the finest level of regulated security. There's no regulations really thus far. So the problem with SCADA is that they can't just upgrade to a new system, because each little piece of hardware still costs about $50,000 to $60,000 minimum, and that's when they're buying it overseas. Most of these systems are not manufactured in the United States. So if you have a system that controls our electric grid and the hardware is manufactured out of this country, there's fundamental security guarantees that you cannot make, because you do not control, you cannot track 100% of that supply chain. There could be microcontrollers in there that could have remote kill switches, so someone in range could send a radio signal to it and shut down the system, or something similar.
So I think most these systems they have restricted access.
Yes.
Yes.
They do have restricted physical access. However, you can go to transformers. There's probably one somewhere around the campus or off campus, and they're pretty much only restricted by a wired fence with barbed wire on the top at most, and they usually don't have cameras. And some researchers here have been working on trying to add more security to the protocols that they use for communication, because currently, if an attacker wanted to, they could go up to it, compromise the machine, and use it to basically take down other machines in a denial of service attack by corrupting the synchronization protocol that it uses to synchronize basically the the phasor functions of the electrical grid. So the problems here facing security are really that these systems are legacy systems in the worst kind. They're installed and they're left there for 50 years. They're rarely ever patched. When vulnerabilities come out and exploits come out, they're not called 0 days, they're commonly called forever days because they never get patched. And they affect national security and public safety. If power grid was to go down, you could have mass rise in crime, and that obviously affects public safety. So remember what happened during the full disclosure days. A lot of things went wrong, but it got the ball rolling. A lot of people got attacked, and it really also got the ball rolling for the malware community. However, if we just hide our head in the sand, would it be any worse? Who knows? Does anyone have any opinions? Yeah.
For these systems in particular, I think that it would be pretty catastrophic to have full disclosure of them, because for the simple reason that you can call it's almost like a form of terrorism on
Exactly.
yourself. It will cause mass hysteria if you just announce there's a severe problem with the subway system in New York City. You're going to cause, the transportation system could collapse in a matter of hours. People would not use things. Stock market would plummet in certain situations for certain things. So I don't know. I think maybe for systems like this, a delayed disclosure could lessen the burden of that, like the impact that it would have, as far as like the widespread panic it would cause.
I agree somewhat. I would argue that disclosure only to the vendor and no one else is the safest bet. This is somewhere like the following examples where you're really affecting people's safety. So let's move on to aircraft radar and control systems and autopilot systems. This year at DEF CON, a presenter who goes by the name of RenderMan presented a very interesting project he's been doing research on that there's a new basically system that's replacing active radar. And that basically planes determine where they are by GPS, and they're just constantly pinging, hey, this is where I'm at, this is where I'm at, this is where I'm at. But there's no security to it, so you can spoof it. So what you can do is you can park a van, he demonstrated, you can park some sort of transmitter outside an air control tower and constantly spoof these packets that there's a million planes around. It's effectively a denial of service on an airport. Imagine what that would happen to the global flight system. All the planes in the air, if that happened for an hour. That would cause chaos and probably cause a plane to crash or two. So he disclosed this months ahead of time to FAA and DHS and all the obviously necessarily interested government parties. And I believe he also consulted lawyers, make sure he's good ahead of time and covered all his bases. But then he discussed all this at DEF CON and showed a small demo. Anyone who was maliciously inclined could probably, even though he didn't release any proof of exploit code, could probably, just having these details, go in, do the research themselves, reverse engineer it, and cause some sort of terror attack. So in systems like this, it's really interesting. The guy did really valuable research, and hopefully someone acts upon it and prevents the next 9/11 and stuff like that. But all the same, having taken credit for it and shown the world, hey, this is what I did, this also causes some bit of a problem. So let's move on to medical systems. Many pacemakers are becoming very sophisticated and have remote power, basically a battery you wear on the outside. And that can be, in concept, attacked through jamming and stuff like that. And even sabotage, even if it were sending it spikes every now and then to basically sabotage the power supply and power system of that pacemaker. That and things I consider like self-driving vehicles really fall into a category where public disclosure of this is what's wrong with this product is really actually doing more harm than it is good, even for your career. Because if stuff goes wrong, then it kind of does come back to you. Yes.
I saw a commercial, I forget who made it, but the guy was on the airplane. He can start his car from his wife or his cellular phone.
Yeah.
And it heats up the car, and then his family gets in, and they're all warm, cozy. But what if something like that, people go around looking for those cars, they can just start them up, steal them, and be on their way.
Replay the signals, basically.
Yeah.
If there's no sufficient crypto preventing that. Yeah, it's true. That in theory can happen. Yeah. You have a question or a comment? Okay. But researchers who do this stuff, I don't really fault them. I applaud their efforts because this is really dangerous stuff that no one really wants to touch. But I do feel safe for the people who are working on this type of stuff. If they're not, some bad people are. So let's get to the actual lecture, which is Linux 101. We're going to cover system administration and attack. If you're new to Linux, basically these are starter tips. When in doubt, consult the man pages. If you're looking for a file, you can use find/-name and then the target name of the file. And if a program is acting weird, make sure it's the right program. Sometimes things get names get reused. Like, for example, the XGUI system has a program called NC, which is the common shorthand for netcat. And if you try to use netcat and it starts giving you weird output, it may be X11's version. So you use which, and then the program name to determine where that binary is, so you can figure that out. So Linux is everywhere. It's on desktops, laptops, routers. It's on mobile with Android. It's in your TV. It's in home appliances, firewalls. It's probably on weapon systems, missiles, and UAV drones, satellites. And it's probably running on most web servers. So an operating system is best described as an interface to the hardware for users. So let's start from the very basics of what happens when you press the power button on a computer. Basically, the PC's power supply brings all the required voltages for the motherboard up to required levels. And then once the good voltage is present, the motherboard will start turning on all the fans and they'll start spinning. And then the clock cycle basically starts and everything starts synchronizing with that. And then RAM should be clear at this point. Non-volatile RAM may not be clear, and that's an important thing to remember. Especially in malware analysis environments, it's important to have basically everything clear from a fresh start so you can start tests knowing that all your systems are good. Otherwise, malware can hide in non-volatile RAM. The processor usually points to the start of the BIOS program. This is hard-coded, and it's usually at that address right at the end of system memory. And usually the first instruction here is just a jump instruction, and it jumps to BIOS code somewhere else. The BIOS performs power on self-test, which is called post, and sees if there's any fatal errors, and if there are, the processor just stops. The BIOS then looks for video card, and specifically it jumps to wherever the video card's own BIOS code should have. And if any other BIOSes are detected along in this process, it executes them as well. What could go wrong here? If there's malicious BIOS code or code at this level, it will get executed without hesitation. Video cards have also non-volatile RAM, and it's very rare, but there have been proof of concept rootkits that hide in non-volatile RAM on specific video cards. However, that's a very, very, very targeted attack. The BIOS then looks for other devices and see if they have BIOSes as well. Infecting BIOS code usually involves a supply chain attack at specific device level. So on and so on and so on. Detects and configures plug-and-play systems, and then it basically looks for the master boot record and starts the OS boot process. There are master boot record viruses.
When you say supply chain attack, is that like...
So supply chain basically means from the point at which all the materials are sent to the factory, the microchips are all manufactured, then they're installed on chips, then they're installed on whatever board, and then they're shipped off to a man in the middle, to various vendors, and they're shipped around the country, shipped around the world, and then they make it to you. That's the whole supply chain. So somewhere in there, that's getting attacked. Usually, the only cases where that happens is nation versus nation. I go into it at the end of the semester, and my lecture on the history of cyber warfare, it dates back to the Cold War. So there's unclassified records of this going on, so I'm not just making this stuff up. The BIOS is ultimately the authority of what is and what's not installed in the system, and this is the basic boot memory diagram. We don't need to go into it much, but it gives a hard look at basically what is located where. So basically, processor points here first, and then jumps somewhere, usually system BIOS code, and then it just goes and goes and goes, reading all BIOS codes. And usually these are jumps to somewhere else, and then they return. So Linux has popular bootloaders such as Grub and Lilo, and they present boot options. Not going to really cover that much. The function start kernel starts the idle process, process schedule, and the init process. The kernel handles all the operating system processes, memory management, task scheduling, input-output, inter-process communication, and overall system control. It is typically loaded as an image file that is compressed with either ZImage or BZ image formats. And Linux is known for having a monolithic kernel. We'll get more into that later because there's a trend now to moving operating system design to microkernels, where the kernel becomes smaller and smaller and smaller. There's less drivers in it, and drivers are pushed outside the kernel. And I'll explain that with this rings model. The ring security model is basically for fault tolerance and security, and it provides different levels of access for things. There are things that operate above ring 0, and that means ring -1 and -2, but it's not represented in this diagram. Ring 0 is the kernel, and for the operating system, that means it has ultimate control over everything. It's commonly thought that root has control over everything, but really kernel has control over everything, but root can do almost anything to the kernel. Ring 1 and ring 2 are where device drivers are. They have most of the same permissions as the kernel. And then ring 3 is where user space is. That's where all applications lie. That's where the init process also lies, and that's one of the first things started up by the start kernel process. So, yeah, kernel space is ring 1 and 2. Most drivers are run here. It's much different from user space. The crash here can be fatal. Random number generation here is very difficult, along with various other things that you perhaps weren't aware of, like handling decimals and stuff like that. Mistakes are very unforgiving in coding here. Kernel modification requires basically recompiling the kernel and rebooting and using the new and selecting the new kernel to use it. However, there are other ways to modify the kernel, such as tools ksplice and kexec. Ksplice allows you to basically modify the kernel on the fly, and kexec allows you to select a new kernel on the fly without rebooting. It is difficult to modify a kernel in an attack chain, but it's not impossible. Now let's get to the init process. It's the father of all processes. It establishes and operates the entire user space, and it takes a parameter, basically run level, from 1 to 6, and it determines which subsystems are run. The main things that init runs is it is populated with scripts to set up all the non-operating system services, daemons, structures, and all the structures for the user environment. It also checks and mounts the file system and spawns the GUI, among other things. And once the GUI is spawned, basically the login screen or prompt is if it's configured to auto spawn the GUI, is presented. Otherwise, basically TTY is presented, and eventually it gets to the login prompt. Let's see. Init scripts are usually located in the etc/rc directory, and the top level configuration file for init is etc/init tab. Usually when you make a modification to this, you have to restart init to get it to reload it. So this is a place where malware can hide at user level. Init spawns all the things every time the system is run. If you want to hide, if you want malware to run every time, you can have it basically set here in init run this on startup. It's not very covert though. Init goes dormant after it has done everything. It waits for 3 things to happen, basically, to do anything. A process that init has started is ending or is dying, then init wakes up. There's a power failure signal, then init wakes up, or there is a request to basically sbin/tell init to change the run level, but you guys don't need to know about run level stuff. There are alternatives to init, such as systemd and upstart and xeinit, I think. That's the old school one. In user space, there are more security levels with the permissions model that's used by Unix, and we'll get into that. Essentially, what you need to know is root is king, if you didn't already know that. It's common to have a single user account per service, so if you have a web server running, like Apache's Tomcat or HTTPD, it will be usually running under its own account when set up properly. Same with MySQL's daemons. And every user account can be set to have no login. So if you try to log in, it may point you to some garbage program like /bin false. And that just returns false and won't run anything. So the file systems in operating systems kind of work like this. This is what something could look like somewhat on disk. Basically, when stuff gets deleted, it gets unlinked and it's left for garbage collection. And garbage collection can happen really at any time. And in the meantime, stuff can get overwritten on it, and that's fine. And then that stuff can get deleted and left for garbage collection. Then something else can be written. So basically, in this diagram, really smooth legs was written first, then the feeling of having was partially written and then deleted, and then your cat was love was written last partially and hasn't been finished. And unless things are securely deleted, this kind of does happen. So these are some basics that you should have learned in your operating system class. That most Linux file systems work like this, that you have a directory entry. It's kind of like a main file table, and the directories have file names and inode entries, and the inodes point to basically an index in the inode table, and that can either reside in memory or disk, usually both. And the inode entry contains a lot of metadata. It contains permissions, ownership info, timestamps, a user ID and group ID, and file size, and most importantly, it points to the actual data on disk. So these block 1, block 2, and etc. point to actual physical locations on disk where the data actually resides. You can have multiple files in directories, different directories, linked to the same inode. This is for basically multi-user systems, say marketing and accounting both need to access the same file, but they call it different things for business logic purposes. If marketing deletes a file, you don't want to have it deleted for accounting. So I'm going to show you what happens when generally things are deleted. That just goes away. And that's about it. It still resides on disk, and the inode and the disk content will be marked for garbage collection, which could happen at any time. And then in this case, when marketing deletes it, accounting's version is still available. All right, so I'm going to go over quickly the generic layout for all the directories in most Linux distros. Any questions so far? Okay. It can be confusing at first if someone hasn't explained it to you. I can go over it pretty quickly. Slash, that's the root directory. It's where everything starts. That's where the file system starts. Do not confuse it with the root account or the root account's home directory. Etsy is usually where most configuration files are. For firewalls, for init, for anything you can think of, the configuration file is probably in /etc. /bin and /userbin. There's no real standardized difference between the two. However, the /bin directory contains more of the most important programs, such as shells that are started when users log in, programs like ls and grep. Slash user bin usually contains other applications for users that have been installed in the system. There's no clear distinction really purpose-wise between the two. Nothing is preventing you from installing something one place or another. You can install something anywhere else you want, really. There's nothing preventing you, but it's just going to make no sense. Slash sbin and slash user sbin are where most system admin programs are. Slash user is where most applications and their source code, where most user applications, source code, pictures, documents, and user configuration files are. Slash user is usually the largest directory on a Linux system, and it also has its own bin directory. That's where the binaries are for these applications in the user directory. Slash lib is where all the shared directories are, and I mean shared libraries. Shared objects are used for programs that are dynamically linked at runtime, and those libraries are stored here. Slash boot, it has all the boot info and also the Linux kernel, and slash home is where all the user's home directories are. Every user has a directory under home except for root. Root's home directory is typically slash root. Slash var has frequently changed variables and also all the system logs. That's very important. Temp is usually world writable by all, and it's just a scratch space. Slash dev has all the device info for a Linux system, and devices are treated like files in Linux. So files you can read and write, and it's just how devices work. Mount is used for mount points, and proc is special. Proc doesn't actually exist. It's kind of like there is no spoon. It's a virtual directory and it exists only in memory, and it contains all the info on the kernel and all the processes on the system. It contains special files that permit access to the current configuration of a system as well. All right. So who's encountered a problem running something on Linux and eventually came down to it was a permissions thing? Should be like everyone in the room. Yeah, they're probably the #1 security feature and also the #1 inconvenience. These are all the common commands. I'm not going to really go over them. You can look them up yourselves in the man pages. But basically, a Unix permissions model boils down to this. You specify the permissions for yourself, the file owner. You specify the permissions for the file for your group. So users can belong to groups. So you specify the permissions for anyone else in your group who wants to use that file. And you specify the permissions for everyone else. These are important. etc password and etc shadow. etc password contains basically login information and metadata about the user. It contains the user's ID for logging in. Password hashes can be stored here. Though they are usually not stored here, and they're stored in the etc shadow file. I'll get to that. It's stored the user's user identifier, which is an integer, and group identifier, which is also usually an integer, and some metadata as well as the user's home directory path, so /home/username, and then the first program that launches when that user logs in, typically /bin/bash or sh, a shell program. If a user account is set to not be able to log in, this can be set to /bin false, and that just returns false. Entries look like this, and as you can see on the end, there's the shell program. There's the username, and X indicates that basically the hash is not stored here. It is stored in the etc shadow file, which has a number of encryption options. Man3crypt is the command you use to look up the cryptographic hash function options for storing your hash. MD5 is no longer secure and has been insecure for a long, long time, though it is an option. The default is DES-based, and I believe it is option 5. No, sorry, this is the default. It can be set to 5 or 6, which is SHA-based. SHA is not DES-based. Which brings us to the least privileged principle. If you have a bunch of services running on a system, You probably don't want them all running on root. If one of those services has a vulnerability and an attacker can attack it and get that system to spawn a shell, it can spawn a shell basically under root permissions. So that allows them to get root. A better idea is to create a user count for every single service that you're running, and most distros ship with most services set up already like this. And many installation processes do this for you as well. Essentially, it boils down to setting up a single non-loginable user account for services. We'll also get into chroot jails. That's another way of keeping processes from accessing things that they don't need to. The least privilege principle is important for security in depth, and also makes logs cleaner and easy to read. If you have things going wrong in the logs all over the place and it's all occurring under root, it's much less informative of the same case where things going wrong and they're all going wrong under their specific user IDs. So MySQL user has this error, HTTP user has that error. So in short, the least privilege principle is basically that you should restrict every entity that's running, every process, user, and program to only the information and resources that are necessary for their legitimate purposes. chroot is a way to confine a process to a top directory other than the file system's root. However, this can be easily broken because it does this by editing the memory of a process. There's a top part of memory where system variables are, and it just edits that. Nothing prevents that process from editing its own memory and changing it back to the actual root directory to escape from that chroot jail. It is seen also as an OS level virtualization mechanism for security reasons. You can see this link below about breaking out of chroot jails. It's not that difficult. Nothing also prevents exploit code from doing this as well. Because either you can call the chroot function, the fundamental function that does this itself with exploit code, or you can jump to that place in memory and overwrite it with something else and then return to whatever your shellcode is. This is a Wikipedia table of all the existing OS level virtualizations out there. chroot is at the top, and there are a lot more virtualization options out there that offer many more system administration and security functionality than chroot. As you can see, the only thing that really chroot does is it partially isolates the file system. As I said, it can be bypassed. That's why it's only partial. Many of these things are actually proprietary, so good luck ever using them unless you work for a big company. But there are things that prevent, that claim to prevent root privilege escalation by isolating root privilege effectively. And that's very interesting. So, as we dive into permissions, files have owners, but there's also things called setUID and setGID. These are used for specific functions and programs that require escalated privileges, but you don't want them being owned and editable by people other than the owner of the file. So for instance, the password function allows you to change your password or change a user's password. It does this by modifying the etc password file, which is owned by root. Now, that means only root, if it's properly set up, only root can read, write, and execute it, and no one else can do anything to it. So if I want to change my password, I either have to ask the system administrator to do it for me, or I use this process that's been set up so that when you execute it, it runs with root privileges, but it's executable by everyone else. Usually when you execute something, it executes under your user account, with your user account's privileges. The setUID bit allows you to set the user account that a process will run as when it's executed, so that if others can execute it, it will execute with that user's privileges. For instance, password is set with a set UID of root, so that when it's executed by any users, it runs with root privileges and thus is allowed to modify the password file. Any questions?
Is it actually running from root, or is it just running with the root's permissions?
Running with root's permissions.
So it doesn't.
Good. Okay. So similarly, setGID for things that require group access to stuff works in a similar way. Basically, if you set something to run with this group's permissions, then if anyone else runs it, it will run with that established group's permissions. So there's a problem. Any programs that have been set UID as root have complete access to a Unix system because they're running as root. Virtually every attack chain on a Linux system involves focusing on attacking these programs. They are single points of failure, and once an attacker gets any form of access, they want to escalate to root. That's always the case. There's a command here at the bottom. This will find all the set UID programs on a system. Here's some example output. About 30 or so programs on a Ubuntu 12.04 system, right out of the box, have set UID with root permission. Some things you perhaps weren't aware of, such as ping. Ping requires network access, and accessing network devices actually requires root access. Many functions actually just call kernel functions to do this. Let's see, another good one. Change shell is just like password. It edits the password file, but changes the shell that is used when you log in. This can also be seen as the attack surface for any permission escalation attacks. And attack surfaces and being able to identify attack surface is something very important to this class, and something we'll be focusing on all throughout. Being able to show people the attack surface for a system is very important to showing them exactly where people can attack and what their potential vulnerabilities are so they can manage risk. This link is a good source for setUID and reading up on that. setUID and setGID are entirely different if they're executed on directories. setGID does nothing, I believe. No, setUID does nothing. It's disabled in almost all Unix systems. setGID basically, whenever files are created, they're created with the group of whatever the GID for the directory is. What am I doing on time? Any questions on permissions so far? Okay. Which brings us to access control lists, which are usually disabled by default but allow for more fine-grained control over permissions, and they're thus very important for security. Has everyone covered access control lists in a previous class? Has anyone not? Okay. All right. So basically, they extend the Unix model where permissions are only defined for the owner of the file, the owner's group and its members, and everyone else. Basically, you can specify permissions for various different groups and specific users other than the owner. It is usually only enabled for root, and only root can change the ACL of a directory. But if you want to enable it for users, say if a user wants to create say a developer in a company wants to create a directory as a shared space for his current team working on some project, you can enable ACL on a partition is a mount option in the /etc/fstab file. etc has a lot of configuration files, and fstab basically means file system table. A typical example of a partition entry with ACL enabled is below. Basically, you have the device identifier. Right here is the basically mount point, the file system. These are the options, and etc. Here you can see there's comma ACL, and that's enabling ACL to be used. So once you've enabled ACL to be enabled on a partition, you have to install tools to modify it. There's two options. You can use the command line ACL utilities or a GUI-based one, such as EIC, IEL. Let's go through an example so you can see how they work. Say we have a file called target.txt, and we want the following people to be able to edit it. Joe, he's the CEO. We want the developers group, developers-G, to be able to edit it. And we want the quality assurance and testing group, QA-G, to be able to edit it as well. Let's say developers-G is currently the group owner for the target.txt file. To enable the ACL, we first run set f ACL, and with the following options. Essentially, we specify that we want to enable it for a group. We specify the group, developers-G, and then we specify we want read, write, and we're not going to allow execute privileges for the file target.txt. Now, say we want to enable it for quality assurance group and Joe as well. In the following line, basically you specify it for the group, quality assurance group, you specify we want read and write, and then we specify for the user, Joe, we want read and write on the file targets.txt. It's pretty simple. However, you should note that if access control lists are enabled, looking at standard Unix permissions with the command ls-l will not show you the access control settings. But if they are enabled for a file, you'll see a plus sign on the end of the permission set right about here. Okay. So access controls are essential really for any large-scale Linux systems. There are also extended file attributes that are important for security as well. Extended file attributes are supported by a large amount of file systems out there. All the Linux defaults, ext2, 3, and 4. And the functions to use and modify them are basically adder, ls-adder, and chadder. There are some really interesting ones. Chadder plus I makes a file immutable. You don't have to be root to use it. And basically it means no one, not even root, can change it, delete it, or link to it. There was a competition that I was in, and it was really useful for trolling the opposition because they didn't know about it. So they had root access on a system, but they weren't able to delete all these things, and they're like, what the heck is going wrong? So it's really important for system administrators in defense to defend things that shouldn't be deleted. However, nothing's preventing an attacker from doing chadder minus I to make something no longer immutable, unless you make something immutable and then you get rid of the binary for chadder, so it locks down the system. Chadder plus A is important for logs. It makes them append only, and that's important. If you have a system and an attacker breaks into it and manages to get root, one of the things you're going to want to do is you're going to want to erase the logs to erase any evidence that they were there on that system. To prevent that is you make the append only to prevent them from going in and deleting specific entries, which is more intelligent for an attacker to do, as opposed to just wiping out the whole thing, which obviously leaves a red flag, which may trigger the system administrator to think to go onto the disk and hunt down for the actual data on the disk, which is completely possible. And then chadder plus S enables secure deletion for a file, which is up. The implementation depends really on the file system. It's different for every file system. By default, only root can use extended attributes, but just like ACL, you can enable it as a file system partition option. So I'm going to get into TTY and PTS, two things that are commonly confused. TTY is basically the terminals that pop up when you have no X environment or no GUI system running. Is named after teletypewriter. I think it's a terrible acronym. Basically, there are a couple commands. Who will reveal all the users in the terminals, whether TTY and PTS, and CHVT allows you to switch to another terminal that requires root. Also, commonly functions, a keyboard combination rather, Control-Alt F1 through F6 will switch between different TTYs. It can be used if your GUI crashes or goes terribly wrong. PTS is a pseudo-terminal slave, also a terrible acronym. Basically, when you're running a GUI and you bring up a terminal, it's a PTS. So you can switch terminals with the screen command. That's very useful. You can split and combine them. Daemons are important to know about, as well as kernel modules and cron jobs, because they're all ways things can be set to run persistently when booting and stuff like that. So daemons, you can view them all with the service command. Service space -- status -all will show you all the daemons running on a Linux system. They're background processes, and typically single function and designed to do nothing else. So syslogd is a daemon that only handles system logging, and sshd is a daemon that specifically handles only incoming SSH connections. Their standard behavior is that they have no controlling terminal. They ignore every signal except sig terminate. They have no open files typically, although system logs and stuff like that can write to things, so that violates that. And they're usually dissociated from any process group. Kernel modules are also very important for security, and we'll get into that later with rootkits. Kernel modules are ways things run at ring 0, 1, and 2, and can be modified, can be loaded and unloaded without restarting the kernel. So it's a way to modify the kernel without restarting and selecting in the kernel again. It's typically used to add support for new hardware file systems or adding system calls, and is convenient for modifying the kernel. Cron jobs are ways also things can be run at user level, and it's usually just for system administration purposes, it's just time-based scheduling to run scripts and stuff like that. However, there's nothing preventing an attacker from having his own script run here and there. And its main purpose really is just to automate system maintenance and administration. Another thing that's important for system administrators and attackers is command history. Just like logs, every command you type in a terminal is logged somewhere, usually in a history file. You can view that with history. You can repeat previous commands with the bash command bang bang, or if you want to repeat the last SSH command you typed, say you SSH into some really long IP address and with some funky ports through some other SSH connection, you can just do bang SSH. And you can print any command instead of repeating it by appending just :p on the end. So logs are very important. Messages is a general messages log. It's usually not used by anything except other users to leave a message for someone. There's the authorization log, fail log, and last log. Those are all the authentication logs. They're very important. If someone fails to log in once or a million times, it's going to get logged there 1 or a million times. Boot log has all the errors and log messages from a boot process. Syslog can be written to various things. Firewalls, such as IP tables, can write here. Daemon log has all the logs for running services, the running daemon services. Kernel log has any kernel errors or log messages, and so on and so on. It gets pretty straightforward past that point. They are usually all stored in /var/log, and that's important. So remote logins, IPs, and domains are usually logged. System modification leaves log messages. Kernel modification leaves log messages. Loading modules and unloading modules also leaves log messages. And daemons modification also leaves log messages. I don't believe cron job modification or a init tab modification leaves any log messages in general. Finally, almost, I'm getting to Linux firewalls, one of the most important ways to control the attack surface on a system for networking reasons. There are two commonly confused things, NetFilter and IP tables. NetFilter was the original project to develop kernel-based connection tracking for the purposes of providing functionality, basically a framework for something else to do firewall management. The firewall management evolved to become this tool called IP tables. There have been various other tools. IP tables is important though. It's for historical reasons as well as it's efficient. So NetFilter is the kernel-based framework that allows for all this. It has three standard tables that it provides: filter, NAT, and Mangle. It's really just primarily a connection tracking system, and it does not do any of the traffic filtering itself. So filter is the default and most basic, and it has input, output, and forward chains, and is responsible primarily for system protection. NAT is primarily for network address translation and masquerading, and Mangle is for other specialized purposes. I'm going to jump into IP tables and we'll discuss basically in more detail here. IP tables has been part of almost every Linux distro since the 2.4 kernel. And there are four main components to IP tables. There are tables, chains, matches, and targets. Policies here are built from an ordered set of rules. Each rule is applied to a chain within a table, and an IP table's chain is a collection of rules that are compared in order, sequentially rather, against packets that share common characteristics. For instance, if they're inbound and outbound, and if they match that, then it triggers a target, which is basically the action. So tables, there are four tables. Three of them are the same as NetFilter's original ones. And raw just is basically for any rules that you can think of that are independent of the NetFilter functionality, and usually it's not used. Filter is really the most important one here, and we're going to go into that. So chains, each table has its own default set of chains when you start it up, and when you first install it as well. The most important built-in chains for us are input, output, and forward. There's also pre-routing and post-routing, but the input chain is for any packets that are destined for the local system. Output is for any packets that are leaving it. Forward are any packets that are running through it, so if this were a gateway or a firewall to gateway, rather. Important chains in the NAT table are pre-routing and post-routing, and this is typically what happens in the kernel and user space when a packet comes in. The packet is handled by the network card, and that generates an interrupt to the CPU, and then the packet is processed, and NAT pre-routing rules are applied, and a decision is made based on the rules whether or not it matches. Then if it's going to this system, the filter table is applied, and the input rules are the input chains are evaluated, and any decisions on that are made, and then it's forwarded along to the local socket. If the local socket sends a packet, it first goes through the output filter firewall, then basically it goes through post routing for any NAT purposes, and then leaves the network card into the internet. And so if it's not destined for the local machine, it stays in the kernel, and it gets forwarded along. So whenever a rule is matched, it has basically an action that's triggered. Typically, it's just like forward it along, or drop, or reject. But match rules are, how do I put this? These are some good examples. So you can match based on the source IP, you can match based on the destination IP, you can match based on the protocol, the interface it comes in on, the interface it goes out of, the state of the connection, that's very important. And also, you can match based on the source MAC address and destination MAC address as well. That's usually enabled by default, I think, in 2.6 plus kernels. So when matches are made, targets are triggered, and basically, like I said, you can accept the packet, you can drop the packet, you can log the packet, you can reject, or you can basically return to whatever called this, this evaluation function without doing anything. In general, the following policies should be established on any system. Any system should be able to make the following queries through the firewall to outside servers, basically DNS requests, FTP transfers, network time protocol queries, secure shell sessions, SMTP sessions for email, web sessions, basically web browsing, and then whois queries. And in general, all other outbound traffic should be blocked unless there's really special cases. Most of the time, it does not. Pretty much everything else does not need to leave the firewall. Then, for things coming in and going out in general, sessions should be basically statefully tracked. Everything going out of the network should be statefully tracked. Any packets that leave the network that do not conform to the state that's currently being tracked should be dropped, and they should be logged. Firewalls should be, by default, be configured with a log and drop policy to guard against any stray packets, port scanned, or unallowed connection attempts, incoming or outgoing. And perhaps should block all incoming SSH traffic if applicable. Like if you're not running SSHD on any of your systems, you're not expecting anyone to SSH in, might as well just block that as well. But you probably want to be able to SSH out, and always want to be able to SSH to the firewall system itself. So yeah. We'll cover this more in detail later, but firewalls are very effective security defenses, and they're a bane to attackers. Ports and services in general can be looked up in the etc services file. And lastly, I'm going to end with, if you've done all these things and protected your system against everything, and someone still manages to get root, they can absolutely ruin your day. And the worst thing they can do is install rootkit, or malware somehow can get installed, and it is a rootkit somehow on your system. The 5 most common ways rootkits get established are through loadable kernel modules. We touched that by talking about modules. Also by hooking, process function hooking rather. Direct kernel object manipulation, kernel object hooking, runtime, kernel memory patching, and so on. But those are the 5 most common. I'm only going to cover 2 right now because I don't have time to finish it, and approaching the end of the lecture. Hooking is a common programming technique that employs handler functions called hooks to modify the control flow of a process. Basically, when a new hook is registered, its address is placed as the location for a specific function instead of that original function's location. So if you call something and it's been hooked, it goes to the hook. The hook can call the original function. It can do anything else. It usually is used to either add on functionality or degrade functionality if basically there's some security flaw in the original function and a system administrator has installed a hook to basically to prevent that area of function, the area of vulnerable functionality from being run anymore. That can be a case. But for attackers, it typically is used for enabling key logging, backdoors, and other shady stuff. Direct kernel object manipulation. So remember how I said proc is a special directory? It doesn't really exist because it exists in memory. If someone gets root, nothing's preventing them from directly manipulating that in memory. So they can use that to hide any process that they run and through either modifying the proc structure in memory or modifying the all proc linked list. And they can use it to hide open ports and other things. Attacks here, however, can face synchronization issues. Basically, if the attack code is running and the kernel comes in, preempts it, and context switch to somewhere else, and then comes back, there can be synchronization issues. Memory can be corrupted for the process table. If it tries to switch to something that's currently being edited, the kernel can basically crash. So sometime later, I'll have to go into kernel object hooking and the rest. But you guys have any questions so far? This was really just a overview lecture. We're going to do the same thing for Windows, and then we're going to proceed through the rest of the class trying to split everything 50-50 Linux Windows, because I think it's important to cover both. It's more difficult though, especially for me. Any questions? Okay, so I'm going to go over two things before I let you go. The first homework's out. It's on the website. Let me go to the website. Website's at this URL. This homework is under assignments. I have it in 3 different formats for you to easily be able to edit. I didn't feel like printing it out because I figured almost all of you are just going to open it up in a Word editor and just edit the actual, text file itself and put your answers in there with the questions, which is fine by me. I'm going to go over the calendar really quick, because I didn't get a chance because my keyboard started spamming random keys last time. So on the calendar here, I've mapped out pretty much in stone all the reading that's required for the course for the entire semester. Anything that's in red is required and can be tested upon. Anything that's in orange is not going to be tested upon. But stuff that I found is really interesting stuff that I think you guys should see. You don't have to, you're not obligated to check it out at all. But if you want to know more about a subject, I've provided these links so you can learn more from good resources to point you guys in the right directions. So I have everything marked out with dates and everything like that. And if you have any questions on it, just shoot me an email sometime. And that's the end of class. All right.